Hi, I'm Mahshid, and I'm presenting the paper Non-Clairvoyant Scheduling with Predictions for SPAA 2021. It's a joint work with my co-authors, Sungjin, Ravi, and Manish. To begin, I want to talk about standard preemptive single machine scheduling. As the name suggests, we have a single machine and we want to schedule n jobs with unknown processing times, P1 to Pn, so as to minimize the sum of completion times. Here, jobs can be preempted and resumed at any time. In the clairvoyant setting, when the processing times are known in advance, the problem becomes offline. And there is an algorithm called shortest remaining processing time, or SRPT, which is optimal. And what it does is that it schedules the jobs in a non-decreasing order of the job lengths. However, in practice, it is unlikely that we know the processing times in advance. In the non-clairvoyant setting, the processing time of a job is revealed only after the job is being completed. This models uncertainties in job durations. There is an algorithm called round robin, which processes all remaining jobs equally and is too competitive. As we can see, the clairvoyant setting and the non-clairvoyant setting are two opposite extremes. But in practice, we can estimate job lengths approximately, for example, based on their resource demands or based on the execution of similar jobs in the past. Now, the question is, can we incorporate such predictions to develop algorithms with better performance and provable guarantees? Here, the challenge is that such predictions can be error-prone. This belongs to the realm of machine learning augmented algorithms. Here, we work with online problems, meaning that input arrives over the time. And we have to deal with the uncertainties that not having the input in advance causes us. There are two main approaches for solving such problems. One is the traditional worst-case analysis that does not make any assumptions on the future input. The algorithms that are developed in this setting are robust and have provable guarantees. However, such algorithms are pessimistic because they consider all input instances equally. The other approach is machine learning, in which we learn from the past and we predict the future. By predicting the future, we are reducing the uncertainties. The problem here is that such algorithms highly rely on the quality of the predictor. Now, the goal is to see if we can bridge the gap between these two approaches. That's why we have machine learning augmented algorithms. We want to use machine learning predictions and traditional algorithm design with the hope of getting better algorithms with provable guarantees. In this setting, we have a predictor having unknown error eta. Eta is a function of input and prediction and must be defined. Our goal is to develop algorithms with two main properties. First, we want to make sure if we are given an accurate predictor, our algorithm performs nearly as well as the best offline algorithms. We also want to make sure if you're not given an accurate predictor, our algorithm performs nearly as well as the best online algorithms without the predictor. There has been growing work in machine learning augmented algorithms, like in paging, scheduling, load balancing, and more. But I mentioned that in machine learning augmented algorithms, we work with an error measure that must be defined. Here, I want to show why defining an effective error measure is pretty important. Remember, our error measure is a kind of way to label the predictions as good or bad. Well, maybe it is impossible to precisely define the goodness or badness of a prediction. But intuitively, An effective error measure should neither tag a good prediction as a bad prediction, nor tag a bad prediction as a good prediction. Let's see it in this picture. Let's assume that light gray ones are the good predictions and the bad predictions are depicted in darker gray. When we define an error measure, it's like drawing an oval in this picture, and the predictions that are within this oval are labeled to be good, and the rest of the predictions are labeled to be bad. So it's pretty important to define an error measure that can capture as many good predictions as possible so we can make use the best of the predictions. Now, let's get back to the non-clairvoyant job scheduling problem, but this time with predictions. This is the problem that we study. We have predictions in the form of job lengths, p hat 1 to p hat n, and all jobs arrive at time 0. Let's see. If we run round robin, we know that it's too competitive. However, round robin does not benefit from the predictions at all. On the other hand, if we assume that the prediction is pretty good and doesn't have an error, the problem becomes offline and we can simply run SRPT on it. This algorithm is called shortest predicted job fares, or SPJF, and it schedules jobs in a non-decreasing order of the predicted job lengths. Let's run SPJF on an example. Here we have n-1 small jobs and 1 big job. And the n-1 small jobs are predicted correctly, but the big job is mispredicted to have the smallest size. Now, the optimal solution is going to run the small jobs first, then it's going to run the big job. And it costs almost 0.5 n square. But SPJF blindly follows the predictions and runs the big job first, and then it runs the small jobs. And it costs almost 1.5 n square, which is 3 times the cost of the optimum solution, and it's not good. So as we can see, round robin and SPJF are two extreme cases. One of them completely ignores the predictions, and the other one blindly follows the predictions. So we want to see if we can do better than round robin and SPJF and provide worst case guarantees. But before I talk about any algorithm, let's see how we can measure quality of online algorithms and online algorithms with predictions. In the offline setting, we know that there is this benchmark approximation ratio, which helps us measure the quality of offline algorithms. In the online setting, there is a similar benchmark called competitive ratio, and it helps us measure how far the algorithm is from the optimal algorithm. Formally, we say that an online algorithm for minimization problem is C competitive on input sequence I if the cost of algorithm on sequence I is at most C times the cost of the optimum solution on sequence I. And it should hold for every input sequence. So far, we know how to measure the quality of online algorithms, but how about online algorithms that benefit from predictions? Here we have two terms, robustness and consistency, to do so. By robustness, we want to ensure that even if the predictions are pretty bad, the competitive ratio stays bounded. And by consistency, we mean that the guarantees of the algorithm must improve with good predictions. Formally, let C be a competitive ratio, which is a function of eta, and eta was our error. We say that an algorithm is gamma robust if the competitive ratio is at most gamma for all inputs and predictions. And it is beta consistent if the competitive ratio converges to beta when the error tends to 0. Now that we know how to measure the quality of online algorithms with predictions, let's bring back the non-clairvoyant job scheduling problem with predictions. This problem has been studied before, and there is an algorithm called preferential round robin or PRR for it. PRR is a linear combination of round robin and SPJF. And here we have a parameter lambda, which means that we give lambda computing power to round robin and 1 minus lambda computing power to SPJF. In this algorithm, they define the error measure as the L1 norm of the job lengths and the predicted job lengths. And they show that their robustness and consistency guarantees is tied with respect to this L1 norm error measure. Another way to interpret their result is that if we want to get O of 1 over epsilon robustness, the algorithm is going to have an additive cost of approximately at most n times the L1 norm error. So far we have an algorithm that uses the L1 norm error measure and gives us tight robustness and consistency trade-offs. But is this the end of the story? Let's first see what limitations the L1 norm error has. I'm going to show it over a similar example. Let's again assume that we have n-1 small jobs and one big job. And let's assume that the small jobs are predicted correctly and the big job is predicted to have the smallest size. So let's see. Here, n-1 of our jobs are being predicted correctly. So maybe it's a good prediction. The L1 norm error here is gonna be 0.01 n squared. And remember that their algorithm has an additive cost of n times this L1 norm, which is gonna be almost 0.01 n cubed. Now let's run a bunch of algorithms on this example. The optimum solution is gonna run the small jobs first, then it's gonna run the big job. And it costs almost 0.5 n squared. SPJF, however, runs the big job first and then runs the small jobs. And it costs almost 0.01 n cubed, which is pretty bad. Round robin almost finishes all the small jobs at the same time, then processes the big job, finishes the big job. And it costs almost n squared. In the PRR algorithm, which was a linear combination of round robin and SPJF, we had this parameter lambda. If we set lambda to 1, the PRR algorithm recovers the round robin algorithm, which is to competitive ratio. So we want to reduce the effect of round robin to see if we can get better than too competitive. Let's say we set lambda to something small like 0.1. So we're gonna run round robin and give it 0.1 computing power, and we're gonna give SPJF 0.9 computing power. The SPJF part does not make much progress because we saw that it's not good on this example. So the main progress of this algorithm comes from the round robin part. And since we're running it 10 times slower than the original round robin, it costs almost 10 times n squared, which is pretty bad compared to the optimum solution. So let's see what's happening over this picture. Here we have a prediction P, which is not bad. It can be good. But the oval that is imposed by the L1 norm error measure, it's pretty small and does not capture this good prediction P, so it does not benefit from it. And that's why the PRR algorithm is having such a huge cost compared to the optimum solution. But how can we better model the prediction error? There are so many error measures out there. Which one should we choose? So here we first identify two natural desiderata that the algorithm measure that the error measure should satisfy. The first one is monotonicity, and it means that the error should get smaller if more jobs are predicted correctly. The other one is Lipschitzness, and it means that when we have a misprediction, the error must change at least as much as the objective changes. Otherwise, the error would not give us enough discriminative power. So we want to define a new error measure that satisfies these two. Let me first define the error measure when all the jobs are being underpredicted. For this case, we define the error as the optimum of the actual job lengths minus the optimum of the underpredicted job lengths. But of course, in practice, jobs can be underpredicted and overpredicted. So now I'm going to explain why we need to be careful with underprediction and overprediction, and why we cannot naively define the error as the difference between the optimum of the actual job lengths and the optimum of the predicted job lengths. I'm going to show it over an example. Let's say we have n jobs having size 1 through n, and the prediction is the same, but in a permuted way. So this is not a good prediction. However, if we want to choose the difference between the optimum of the actual job lengths and the optimum of the predicted job lengths as the error measure, it's going to be 0. So it's really important to take underprediction and overprediction into consideration when we define our error. And that's why we have this complete version of the error measure for all cases. Now, let's see what our algorithm does. Before I explain the high-level idea of our algorithm, I want to pinpoint that the challenge of our algorithm is that there is a discrepancy between actual error and the error we perceive before completing all jobs. Because remember, we don't know our error until we have finished all of the jobs. So I'm overly simplifying our algorithm, and basically it is an iterative algorithm. And at the beginning of each round, we estimate the median of the remaining job lengths. How? By sampling a few jobs and processing them by round robin until half of them are finished. The last finished job length is the median. After that, we compute the error of the jobs that we finished in step 1. If it is too big, we process all jobs up to median by round robin. Otherwise, we process all jobs that are predicted to be smaller than the median using SPJF up to the median. I'm going to bring back the previous example and let's run our algorithm on it. So here, remember that we had n-1 small jobs and 1 big job, and the small jobs were predicted correctly, but the big job was mispredicted to have the smallest size. Our error here is going to be, because it's an underpredicted case, our error is going to be optimum of the actual job lengths minus optimum of the predicted job lengths. And it's going to be almost 0.01 n squared. Now let's see what our algorithm does. We first estimate the median lengths of the jobs, which is going to be 1 with high probability. Then we run SPJF on all unit size jobs up to unit size. After that, we finish the remaining big job. So our algorithm first finishes the small jobs and then finishes the big job. And it costs almost 0.5 n squared. And the optimum solution also runs the small jobs first and then runs the big job, and it costs almost 0.1 n squared. It is not by accident that we are getting the optimum answer here. Here, we have a much smaller error compared to the previous one, like the one for the PRR algorithm. So our algorithm is forced to give nearly optimum solution. And remember that the PRR cost here was almost 10 times n squared, which was pretty huge compared to the optimum solution. And that was because they have an additive error that is n times the L1 norm error and was huge, for example, for this example. So to compare the two algorithms, I mean the PR algorithm and our algorithm fairly, let's say we want to have 1 plus epsilon opt when the predictions are almost correct. Then we show that PRR has always an asymptotically worse additive error than our algorithm. So to recap, we propose an error measure that more faithfully distinguishes between good predictions and bad predictions. And we developed a better non-clairvoyant algorithm with machine learned predictions. There are some interesting problems that we can study from here. First of all, even though our algorithm has a better asymptotic guarantee, it has pretty large constants hidden. Improving the hidden constants could lead to more practical algorithms. One of the reasons that we have a large constant is because we use randomization to estimate the median and the error iteratively. We suspect that there could be a deterministic algorithm with better guarantees. Also, in our result, we assume that all jobs arrive at time 0. It would be interesting to extend the work to the setting where jobs have different arrival times. That concludes my talk. Thank you.